Good morning, everyone. Time to pretend you're awake. Chat has already been talking about how long ago it was when they actually woke up. Someone has used a bed emoji to say that they're still in bed. I find it quite funny that we used to be like this about 9 a.m. lectures. We'd be like, oh, I've got to drag myself in for a 9 a.m. lecture. And you'd be up at like 7 to drag yourself into UNSW for a 9 a.m. lecture. And now it's like, oh, I had to turn my computer on at 9:55 for my 10 a.m. lecture. But we're also like recalibrated for lockdown that 10 a.m. is now officially a struggle. I was thinking to myself sometime very late in the evening last night that I think I would have delivered a more effective lecture at say midnight to 2 a.m. last night than I was going to at 10 a.m. this morning. But that's the way it goes. That's the way it goes. UNSW is obviously still attempting to run on real human time, which I know only some people are capable of still doing real human time. I, for one, have embraced lockdown in a way that maybe is uh, not entirely necessary, but it's happened. So I'm just gonna roll with it. Oh, um, so for those of you who are still in bed right now, um, wake up, wake up! It's time to learn things. La 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 la. Okay. I was thinking of putting on the song "Wake Up" by Rage Against the Machine, the one that's on at the end of The Matrix, which is actually, I haven't put that in the reading list, but it's potentially something that we could look at in terms of turning point CG films. I don't know if technologically I'd have to really look into it, but I know that culturally it was significant, but I'm not sure if technologically it was a significant film. But that would have been a very, very interesting, uh, very interesting wake up call for those of you who are just right this moment on your phone, maybe, and plugging in your headphones to tune into graphics. Um, Noticing from the number of people that are online right now, I think there's a general reaction to the 10 a.m. lecture, so I'm expecting this to just get viewed after the fact by a lot of people. I noticed that for the last one, at least people are watching the lectures within kind of the 24 hours of it being live streamed, and I would recommend that you stay on top of things. I know that I'm being reasonably friendly with the lectures and saying I'm not there's not like marked attendance or anything like that. But the tutorials are going to follow from what happens in the lectures. So I would recommend that even if you can't necessarily watch the lecture exactly when it happens, to still try to get through the lectures before your tutorial that week. Which is hard, I guess, if you've got an early Wednesday tutorial and it's the Wednesday lecture. But then your option obviously is maybe you can get up for a 10 a.m. start. I know it sounds so brutal and uncivilized nowadays, but remember, it wasn't that long ago where something like a 10 a.m. start was considered a cruisy morning, and we were totally okay with doing that. We can do this. We can do this. If there's something that we're really going to put our hearts and minds into and put all this effort into, it's going to be waking up and being functional at 10 a.m. I'm sure you can. I believe in you. I believe in you. Hexus once had a bunch of people in the PC Sock stayed up for the Apple event last night. I didn't realize there was one. Um, but I assume Apple is announcing a whole bunch of new things they're doing and stuff like that. Bob's asking, is it too late to swap tutorial time? I don't think it's too late. I think all of that stuff is still open at the moment. If there's space in other tutorials, I think you can still move things. Anyway, I'll let the tutors answer those questions. I don't want to get too caught up in chat. So, let's get into what we're talking about today. So, Monday, I was talking very conceptually, if anything. Actually, I'm still quite conceptual today. But on Monday, we talked about the history of computers, and we talked about basically kind of talked through the course outline. I'm keeping the course not too complex in terms of like all the bits and fiddly bits that you need to do. But today what we're going to do is we're going to start getting deeper into how computers actually make graphics. So how do computers show us what comes out on our screens, specifically in things like games. So we're talking about often 2D or 3D environments and stuff where a lot of movement is happening on screen and things like that. So we're going to look at the hardware. We're going to look at the important pieces of hardware for graphics, which is the monitors and the graphics processing units, or the graphics cards, you could call them. I mean, I focus more on the GPU, the actual processing unit on the card today. But we'll go into more detail on a lot of these things as we go along. This is not going to be a deep dive into the hardware, but it's going to be enough about the hardware so that you have an understanding of how it works. I stopped short of getting a microscope image of the GPU die and pointing out the bits of it and what they mean, because if I do something like that, I'm likely to get it wrong anyway. You know, we're approaching this from a programming perspective where we have to understand what our hardware does for us, rather than exactly how the hardware would have been built or how it works. Simon's reminded me, and this is a good thing for me to say, the tutorial code, we understand that some people had issues getting through to GitLab and getting authenticated on GitLab to download the tutorial code. So for the moment, the tutorial Git repository is publicly available. So basically you can just download it. The link will be... Actually, I'll show you later because I have the course website open and the setup open. I'm going to talk through that later. The link is actually later in the slides, so you'll get that later. Actually, I don't know if the tutorial link is in the slides, but the other setup links are in the slides. Either way, the links are available on our course website. Yeah, so in case there's no... in case there's... you're having trouble accessing the code, we should make sure that everyone can get the code. And then if we can get everyone's like login issues sorted out, then we'll return the repository to being students only. There was a question also about recording tutorials. At least one tutorial will be recorded each week. So that way, if you miss the tutorial, you'll still have access to sort of catch up. If you want to, you can go back and watch it. Okay, so I was talking about hardware. We're going to look at what is the monitor and how it works, and we're also looking at the GPU. I actually forgot, there should have been a point there. Oh no, let's... There you go. I do like the fact that this time I've decided to use to give you a direct link to my Google Slides. So if you're watching now, you don't have to re-download that for me to put that little edit in that I decided to say there. And also, I don't know if... Actually, I do know that some people have been watching that you get to watch me make the slides. So you know how prepared I am for this. Usually less than 24 hours. I like to do my final prep for the lecture less than 24 hours before the lecture, so I actually remember it. And then, like, I know... I was like, I've gone through the slides in depth, and I'm just like, I know exactly what I want to say there. GPU is a computer inside your computer. We'll talk about that in a moment. Funny stuff. There's actually a historical reason for why the GPU exists. And I did some maths on it, and apparently it is still a valid reason for why the GPU exists, even though it's a reason from the mid-90s. But yeah, it's only one of the reasons. We'll talk about that later. And then we're going to talk about what is rendering. And this is a huge question, because rendering as a blanket term is just turning something into a particular form of itself. I mean, because like the term. Oh, let me just move the camera a bit. Someone has come along to say hi and to supervise and say hi to everyone. Um, so rendering, you can talk about rendering even when you're not talking about computer graphics. Like rendering is something you can do with animal fat and things like that. You know, like I think they use a rendering process to make soap and things, right? So it's an old term for, yes, converting something into another version of itself. But what we're going to be doing is a process called polygon rendering. And your Hexus one says rendering is when you pour concrete into a mold. Oh, so maybe rendering the soap is the solidification of it. And I do understand that that's potentially why it's rendering with computer graphics, because we're taking a virtual possibility of what something is and turning it into something that is concrete in terms of like, this is what appears on the screen, and this is what you will see when you're viewing something. So that's, I'm yet to find out. You may have noticed that, as opposed to previous courses you may have taken with me, depending on when you took the courses with me, some of them had slides that were like a year old by the time I taught it to you, and so I tuned them. I have a slight fear that today's lecture I've tried to squeeze too much into it, but we'll see how we go. Because me saying I'm going to teach you all of polygon rendering in one lecture is a very far-fetched idea. So what I'm going to be teaching you is an overview of part of the process of polygon rendering, and hopefully it'll be enough so that you get an idea of what we're doing. And the idea is enough for now. And remember, we'll fill out the gaps as we go. Simon's giving us the actual some actual definitions, like rendering something useless is rendering is like to end in, so it's like finishing something, I guess. Well, not finishing. Finishing is not even the right word, right? Bring something to its final state. This is not even my final form. Anyway, yes. Okay. So we're going to talk about rendering. We'll see how long that takes me. I want to go through this in a way that you understand it, so that when you start implementing it, you know which part of the process you're actually working on. Then we're going to have a quick look. It's going to have to be quick at just even talking about what OpenGL is and what shaders are. We're not going to get into that much detail on either of these things today. But again, we're going to be coding these things. I'm going to let your tutors teach you more about the specifics of these things, but I need you to know at least that this thing exists, and it's the thing that we're using to code in the subject, and specifically, how are we coding in the subject. So we do have a coding setup. We've sent some links around previously, both in your student email, which hopefully you're checking, on the web CMS, which you should definitely be using. I mean, if you're here in the lecture, it means you found the link to web CMS. And also I've got links in these slides as well. So everywhere where I have communication with you about this subject, I've spammed links for the coding setup for the subject. There are also some videos that help you get set up. There are what I found to be clear instructions on the setup in the Git repository for the subject as well. But we'll get into that. I think we'll get into that when we get into that, because I've actually got the setup done here, and I made sure that I had nothing going on this computer and set it up from scratch. But we'll talk about that when we get there. Okay, so let's get into the first thing that we're going to talk about today is computer monitors. I put this image in here on purpose because the Trinitron monitor from the 90s just gave me such a blast from the past feeling that I thought I'm gonna put this in, because I was gonna do something really silly, right? I was gonna put a picture of a monitor on the slide, and then I was like, if anyone's watching this lecture, they can see a monitor. I mean, maybe it's a tiny, tiny monitor like this, but it's still a monitor. Calendar notification, you have a lecture at 10 a.m. If I've missed that one, there's a problem. I thought it'd be really funny to show you a classic. So these things, where are we capping out? Somewhere at 800 by 600 pixels. I think you could get them up to 1024 by 768 near the end of their lifetime, and end of their kind of product cycle. The cool thing though is, before the era of LCDs, these things were pushing 100 to 120 hertz refresh rate. So anyone who's like, really into high-end gaming hardware, and they expect their LCDs, their new powerful LCDs, to run at 144 frames a second. These things were doing this in the 90s, even when they had, very few pixels, and all the color from the pixels was bleeding into each other and all this kind of stuff. So very, very interesting. But let's boil it down to exactly what a monitor is. So a monitor is a physical device. So physical devices, I mean, as opposed to what's inside the box in your computer, which are also, everything's a physical device. But this is something that's designed to interface directly with the human. So big two-dimensional grid of lights. Lots and lots and lots of little lights in a rectangular grid. Those little light sources come in many different forms. The majority are liquid crystal displays with backings like LED and OLED. There's a lot of different names for them nowadays. There's like the mechanical process at which they send the light out to you. There's IPS panels or TN panels and stuff like that. If you want to delve into it, you can find monitor enthusiasts who will want to tell you every little thing about the details of these. And there's a cathode ray tube. This is old tech, but the cathode ray tube is what's in one of these and in old TVs and stuff like that. If you ever see anything that's not flat and that actually has like depth behind it, like this thing is nearly longer than it is wide. It's because the way that they work is they have a glass screen at the front with actually a metal mesh behind it that gets a beam of cathode. Gets a cathode ray. I don't know that much about it, right? But it's a beam that gets fired from the back to the front, and that beam, using a series of magnets, gets waved across the lines of pixels in the front of the monitor, activating them at different levels, and the different amount of activation on them changes the brightness and color of the individual pixels. The cathode ray tube's that beam's only capable of hitting one pixel at a time, and so it used to go across one line after the next. And that process, I'm just adding a little info here, is called rasterization, like one line at a time. And the funny thing about it is, even though our LCD monitors nowadays are capable of just flipping all of their pixels in one go, the order that we send information to the monitor is still that same protocol. One pixel at a time, left to right, one line at a time, top to bottom. Simon, are you looking this stuff up, or do you know this stuff? This is me testing my tutors, right? I'm pretty sure he actually knows all this stuff. So either that, or you're just Wikipediaing really quickly. Simon also said you could go outside and see your friends in the nights. But anyway, live chat, Simon's actually dropping the facts there if you want to. So the actual tech behind the cathode ray tube. So I dropped this in without actually going through and reading everything about how that worked, because it's not actually relevant to what we're studying. I just put that in there. Okay, so this two-dimensional grid of little lights, each one of those little lights is called a pixel. And each pixel has a separate red, green, and blue capability. So last lecture, it's only 2 days ago. Well, I mean, we've been in COVID-19 for the last 20 years, right? Last lecture, I told you about the red, green, and blue thing. how our eyes have 3 different types of receptors in them, and each one is tuned in on a particular wavelength of the electromagnetic light spectrum, and that is the wavelengths for roughly red, green, and blue. We have set up the idea of specific wavelengths for red, green, and blue. There is actually a museum, I think it's in France, that maintains the metric standards for things like red, green, and blue. And so they have a particular nanometer wavelength for each of the portions of the spectrum that are named specific colors. Like there is the official green, I think at 600 nanometers. I'm just pulling that out of my head. I know it exists, but I don't know the actual numbers for it. And your monitor will be sending out those colors at reasonably close to those exact conventions for what the colors are. Like, I'm only going to say reasonably close because I know we've all got lots of different brands of monitors. Different types of construction of monitors is likely to have different variants on how accurate it is for colors. Like, you know, digital artists, the people who are making the content that then comes to us as programmers to then put in something like a game or a movie, they're often using monitors that are worth thousands and thousands of dollars because of their really, really exact perfect color replication. It's funny because if you're a gamer, often you'll want a monitor that just sends a signal out really, really quickly. So it just says, the signal comes from my PC, I get it on screen really fast because real-time refresh rate is more important to you. So it's interesting how it goes either way. So red, green, and blue capacity for each one of these little lights. Those lights are also refreshed, so that rasterization process happens multiple times a second. I would say nowadays that the slowest monitors that we have are going at about 60 frames a second, so 60 hertz. And that's actually kind of what I consider the standard at the moment. I'm not sure how many are still like this, but plenty of people's TVs are still not going at 60 hertz. They're going at the standard TV and film refresh rate of 24 frames a second. Which is quite funny because that's been a standard for a long time as being the reasonable, necessary number of frames per second for people to see movement. And I'm saying the standard is somewhere around 1920 by 1080 pixels, so that's the literal number of separate little lights in your monitor at a certain number of bits for the color per pixel. So we're in like 2 different spaces here. We're in this physical space of the actual bits and pieces. I should not have used the word bit there. The physical space of actual pixels. And then we're in a digital space here by talking about the number of bits per number. So the information that's going into how much red, green, and blue is in being displayed in each pixel it's just an integer, right? It's just a certain number of bits integer. And so you'll see you'll see people sort of advertising different monitors, different capabilities. Like a lot of us nowadays are running 2560 by 1440, so more pixels on screen, which gives us a kind of higher fidelity for the picture. 16 to 24 bits is pretty standard, so 24 bits has become the kind of new normal for color because it's quite easy to manage because it's 3 8-bit numbers for your red, green, and blue, which is very, very convenient because computers like working in powers of 2. So 16 is super awkward because it's basically 5 bits per number, and like, who wants to work with 5-bit integers, right? 60 hertz is the minimum, but a lot of us are trying to run things at 144 hertz now at the moment. Someone's talking about college. Yeah, I am actually letting my lectures go out public, so there may be people who are just hopping in and watching. So hello, welcome. Okay, so that's what our monitor is. It's capable of doing those things. I haven't talked that much about the back end of the monitor in terms of like what tech is necessary to get these pixels actually lighting up correctly. I don't think that's super important, but if you want to, you can go and look this up. Again, I'm not talking today, when I'm talking about the hardware, I'm really not talking from a sort of like a electrical engineering or even a computer engineering perspective here. I'm talking about it from the perspective of a graphics programmer, what we would like to know about these things. So, a little bit more about how these monitors work. I love saying this because like none of it is real, right? So it's really interesting to think about how these monitors work and how they display an image to us and how they're very, very specifically working on humans. They are an illusion of the vision that we might have in the real world that literally only works on humans. If you were to perceive the world in a mildly different way from the way humans do, then the computer monitor does not work for you. So it's really, really interesting how it ends up being that way. That the monitor is not a representation of an actual image. It's just a big trick. The idea of showing humans things, the idea of what we call smoke and mirrors, which is all this stuff that was like old theater tricks from like the Shakespeare's era, 1300. Wait, 1300s? Do I have that right? Okay, history's flaky, but you know, sort of medieval era tricks to get people to believe something. We're still just tricking people into believing things. So color in our computer monitors is not real color. It is a specific ratio of red, green, and blue, and that matches up precisely with the red, green, and blue receptors in the rods and cones in our eyes. Other animals that don't have the same red, green, and blue receptors are not actually going to see the same thing on the monitor. I mean, depending on the size of the pixels, once the pixels get small enough, these colors sort of bleed into each other. But even as they bleed into each other, they're not genuinely sending out a particular wavelength of color. They're sending out an exact mix of red, green, and blue. And so here we have some pixels in different different technologies. So there's the CRT monitors are saying, and two different kinds of LCDs, which are the monitors we're more used to using. Each one of these squares is a 1 millimeter worth of pixels. So someone put this together on Wikipedia and thought, oh, that's really interesting. Because what we see is not the genuine color. What we're seeing is a mix of red, green, and blue. So when we're looking at our computer monitor, 1600s. Thanks, Simon. Simon, you're like a human encyclopedia. This is really handy. You're going to end up having to do all the lectures from now on. Amy said Mark isn't real. So it's like, this is just an image of me on your computer, right? Anyway, what we're seeing is not the actual color. We're seeing some mix of red, green, and blue that triggers our eyes the right way to see the right color. We're also not seeing complete objects. We're not seeing real objects. We are only seeing the illusion of real objects, because any object that we look at on a monitor is a series of square chunks, basically, of RGB colors. That's why they call it RGB, because like all the LEDs in our computers are done with this kind of red, green, blue. Actually, I don't know if the LEDs are a mix of red, green, and blue, or they use the red, green, and blue numerical system to send the color to the LEDs in our computer. So the LEDs making our computer look spiffy, like these, might actually be genuine wavelengths of light. I don't know. So all we're seeing is a series of square pieces of color, and that color's not real color, but we're seeing square pieces of color, and our mind is putting together the idea that that's an object. So based on the contrast between colors with all these little squares next to each other, we ourselves as humans create boundaries between objects. So even just here on my screen here, there's some dark grayish color here, and there's white color around it. myself as a human, and yourselves as humans, we're very good at detecting the boundaries between colors, because contrast color boundaries between things tell us that an object is separated from another object. And so all we need is this to be a pale color and the dot to be a dark color, and we say that's a dot, and we identify it as a piece of something. Whereas if we were to zoom in far enough, it's just a grid of RGB things, and these have mostly bright and these are mostly dark. You know, there's no actual object there. There's just the illusion of the object based on which pixels are lit up. And the illusion of movement is like kind of one of my favorites. So I want everyone to think of a game that you've played or a movie that you've watched, and think of one of the most dynamic scenes you've ever seen. Like people are moving around, or like a fight scene in like a Marvel movie or stuff, and there's all this dynamic movement and all this kind of stuff. And then think of this. I want to give you a statement that is actually a true statement. But it kind of, like, whenever I say it usually shakes the foundations of what people see. Nothing in any film or any game, and I think I'm right in saying this, that I can say this as a blanket statement, nothing has ever moved. Nothing has ever moved in any computer game or any film. So, for films, if it's live action, the source material was definitely moving. But what we were doing when we recorded that source material was taking a series of still photos. And on our monitor here, we're displaying a series of still images. I'm not moving. Oh, I'm moving here. I'm moving here in my house, but none of you are here. It's just me. I'm the only one that can see me moving. The only thing you can see is, depending on the frame rate of your YouTube stream at the moment, you're seeing a series of still photos taken of me, but they're being played back so close to each other in time that we accept that movement. We, as humans, and with our highly complicated brains, piece together each image one after the next and believe in the persistence of objects between one image and the next. If we didn't have this belief, it's more than a belief, it's like physiological, but if we didn't have this concept of persistence of objects between us seeing something from one point in time to the next point in time, this could be 60 different marks per second. We could be seeing 60 different marks per second, but we're not. We believe that it's one mark that is continuing to move between frames. So that's how we're able to display a series of still images in a row and get the illusion of movement. So what our monitor is doing is a highly elaborate technological trick on humans to get them to believe color, activating the rods and cones in particular ways. The pixels are close enough to each other in a vaguely rectangular grid, so that when they're close enough to each other, we see the boundaries between large sections of color instead of seeing the individual pixels. You can see this in something like pixel art, which is blown up in size so that you can see individual pixels. It's a throwback to a previous era of graphics, that when you can see individual pixels, it's harder to make something out. So the illusion of objects, and then the illusion of movement by placing similar images next to each other in time, right? So the whole point of the monitor, and this is quite important to us in graphics, because this is everything that we're going to be doing, is working with these illusions. And so everything that we're going to be doing is going to be tricking people into believing these illusions. So let's move on to the graphics cards. I think I talked too much about that, but it's just so exciting and interesting, right? Oh, Simon's also saying that, like, the brain sees images upside down and reversed. I'm not going to go back to the slides, but I showed you the slide of an eye on Monday, and the way that the lens works in the eye is like light comes in and it goes kind of through, and so the thing on the retina is actually upside down, and we in software change that image to something that we understand as like what is physically up and down. Okay, let's talk about graphics cards. So I thought this was quite funny, right? So I showed a 1990s computer, and then I showed the latest and shiniest as of right now graphics card, the RTX 390 by NVIDIA. So I went straight to their website and pulled a photo of that. This doesn't tell us much. It just tells us that the housing for a graphics card is a big chunk of like metal and plastic. So we want to talk about what it actually is. So I like to sometimes call it a computer in your computer, because the funny thing about it is when we think about computers, I'm pointing at my computer here. I'm just going to aim my camera across so that when I point at it, you can see it, right? This big thing here, this big circular thing, is a fan above my CPU. And the CPU is known as the central processing unit. It's the thing that we send instructions to when we write computer programs, and it executes those instructions, and then some result happens. There's also memory in our computer. See these things with like the light falling on them? Those are the LEDs on my RAM chips, because that's not excessive at all, is it? That's perfectly necessary for computer memory to run, to have lights on it. I just like showing off my rig. Your GPU has that all inside it. So your GPU has its own RAM and its own processor, which is interesting because like you look at them and go, why are we duplicating hardware? Why do we have a different piece of hardware in our computer that obviously is doing something different? We need to think actually about what it's doing. We're going to talk about that later. But why are we replicating something that potentially could do the same thing? But we'll talk about that, because they do the same thing, but they do things in a very different way. We're probably not going to get into that in too much detail today, because what I'm trying to do is squeeze in an overview of the concept of the entire course today from a technical perspective. Like, Monday was from a human perspective, like the cultural effect of graphics on the kind of pop culture zeitgeist, as I would call it. But now we're going to go, all right, we didn't just come here to study the history of computer graphics. We came here to study how it works. So we're going to talk about the graphics cards themselves. They get data through the motherboard. So this, I moved the camera and then I pointed at it again. Anyway, my graphics card here is plugged into what's known as the PCI Express bus, which is something on the motherboard of the computer that is able to transfer information. Anytime you hear the word bus, when we're talking about hardware, it's usually something that just sends bits back and forth between devices. So there's the RAM bus, which allows us to access the RAM chips, which are physically separate from the CPU. You know, there's little pathways between them on the motherboard. And there's a similar set, but different set of pathways between other parts of the motherboard and the graphics card. And that's just standard data transfer stuff. I think if you're interested in this kind of thing, you're looking at courses that are a lower level. When I say lower level, I'm talking about the hierarchy of computing, where it's like abstract computing is like theoretical mathematics, and the lower level is closer to hardware. I'm not saying that I'm not making a judgment when I say higher or lower level like that. I'm saying that these are like talking nitty gritty or talking like highfalutin concepts. So I think there are courses in computer engineering and electrical engineering that go into how this stuff works. So it's kind of like graphics is actually reasonably high level. We understand the hardware exists and we're going to use it, but we're actually coding in a high level language, C++. We're not actually getting into like assembler or anything. Although, I'm going to talk about this later today, we are actually talking about code that gets copied to the graphics card and runs on the graphics card. Again, we have to get to that as we get to it. So, it receives data from the rest of the computer through the motherboard, from the PCI Express bus. Depending how far back you go in time, you may hear about things like the AGP bus or even the PCI bus, but I don't remember any graphics cards. I think actually maybe the earliest graphics cards ran on standard PCI, which doesn't even exist anymore. I think PCI Express has replaced all of the other buses for add-on cards and computers. Okay, the only outputs, I'm going to put these in quotes because it's not the case in general, but it's the case for us. For us, the only output from the graphics card is going to be the computer monitor. So the primary output for the graphics card is the monitor, which is why we're talking about monitors and graphics cards. And I understand this is not the case. I'm disregarding processing on the GPU for the moment. And I know plenty of people are using GPGPUs, they call it. What is it? What does it stand for? General processing on the GPU, I think. To do things like machine learning, to mine bitcoins, to do data analytics and stuff like that. But this course is not worried about that. This course is specifically following like a one-directional pipeline. CPU and RAM give information to the GPU. The GPU uses that information to turn things into pretty pictures, sends the output directly via a cable to the monitor, and then the monitor lights up the right pixels. So the GPU is going to say, these are exactly the numbers I want in all the pixels, send that signal to the monitor. The monitor makes all the pixels light up the right way, and then we understand it. Simon said AGP is Advanced Graphics Processor. So the AGP bus was specific to graphics. Oh, GPGPU is General Purpose Graphics Processor Unit. Yeah, so that's the term they use for running programs on the graphics processing unit that aren't graphics, but they're going to come back to the computer as some kind of information, often numerical. The GPU is very good at numerical stuff. So why does this separate piece of hardware exist? So let's do some numbers, and this is a fun bit of numbers. So let's try to, and I've actually updated these from the modern day because this number calculation here existed in an earlier era, which was one of the reasons why separate graphics cards were invented. But I've updated the numbers for the modern day, and strangely enough, it still works. So let's look at our monitor. Sample monitor, not even that high-end a monitor here, what I'm talking about. Hopefully I got these numbers right. I just punched them all into a calculator and added it up, and it was like, this is what I think is happening. 1920 by 1080 pixels. That's a lot of pixels. So it's like a few hundred thousand. Approximately 200,000 pixels. At 24 bits of color means 6 megabytes. So if we're not compressing that in any way, and if we were compressing that, then how slow would our monitor be? And we would need a separate processor in our monitor to decompress that data. So we want this monitor to be quickly giving us what the graphics card is, because one of the worst things we could have with humans involved is a lag in time between when I say move my mouse here and when the mouse moves on screen. So if I'm moving my mouse physically and then the cursor's not following me exactly, or is slightly delayed, our humans get thrown off by that big time. Oh, I'm also a human, just in case anyone was wondering. Beep boop. Robo lecturer. Anyway, yeah. So this is approximately 6 megabytes of information. So what we're going to need is 6 megabytes of information for every time we refresh the frame in the screen. If we're going to do that 60 times a second, that is approximately, and so this isn't exactly 6 times 60 because this is approximation of this actual number, gets us to around 365 megabytes a second needed to keep refreshing the monitor. The interesting thing is the PCI Express bus, which is the thing passing information around on our motherboard. It's not the only thing. There are actually faster buses that would have been able to do this. But if we assume the PCI Express bus is the thing that gets us kind of out of the CPU's kind of dedicated space and into something that can interface with other hardware, that thing goes at 266 megabytes a second. So we're literally not capable of refreshing a monitor at its standard pace, which is super interesting, right? I mean, like, look, if this was a real issue, and we really needed this to work, we would have just built a different bus. right? We would have built a different bus that goes to the monitor. But historically, we did something else instead, where we said, oh, why don't we have something that handles the display stuff, and we'll get that separate piece of hardware to hold this 6 megabyte thing, and then go over a really fast physical connection to the monitor. And this 6 megabytes of stuff going at 60 times a second, we will only send important changes to it, and then it will handle what those changes mean. So this 266 megabyte a second isn't enough to send through important changes to the graphics card. Then the graphics card handles the fact that you need 365 megabytes per second worth of data going out to the monitor itself. So the graphics card then handles all of that stuff on its own. So it's interesting how the initial problem got us a separate piece of hardware, and then this separate piece of hardware has just kind of taken off on its own. And I would argue potentially that, depending on your computer, that the graphics card actually has more processing power than the rest of your computer, because we've put so much time and effort into making these things work. So it's interesting that back when the hardware was first created, the numbers were closer to 640 by 480. They were much lower, but the same argument happened because they were lower, but we had slower buses. I should also point out that if we were to want to send images to our computer another way, the RAM bus on our computers, as in how fast we can get information to and from our RAM, is going in the order of like 15 to 20 gigabytes per second, which is totally enough to do this. So if historically we hadn't decided to create separate GPUs, there's a possibility that we wouldn't need them at all. So nowadays, some motherboards have a very small GPU on them that does the same thing as a separate GPU. Most modern Intel processors actually have a small GPU on the chip itself. So inside the CPU, there's a little section of it which does graphics processing, and then that talks to the motherboard and sends the monitor output directly. Plenty of people are using those. Integrated graphics totally works. But when we're talking about high-end graphics and stuff, we're more likely to see a separate graphics card. I think there's very few people who are playing things like 3D games and stuff like that without a dedicated graphics card. But okay, that's not the bandwidth issue is not the primary reason nowadays why we have a graphics card. The graphics card is there because it does something different from the CPU. So let's have a look at it. Because like what I said before is like it's a computer inside your computer. But let's not start thinking that these computers are the same. The CPU and the GPU work in very, very different ways. And so I have some numbers here and some just general idea of the difference between the capabilities of these things. So I took these numbers from the current stats of the high-end hardware that is in a lot of computers nowadays. So regular CPU, if we look at the reasonably new Intel Core i9 processor, it has 8 processing cores. I mean, I know it's capable of doing more than 8 things at once, because it's got things like hyper-threading and like can run cores as if they're 2 cores. But anyway, physically, 8 cores at once, running at 3.6 gigahertz. So running very, very, very fast, doing 8 things at a time. Anyone who's done a bit of like microprocessors or operating systems and stuff like that, or even just any course that's done threading, will know that you can run multiple parts of the same program on separate processors, or you can run completely different programs at the same time. I mean, we take it for granted. So at the moment, I don't know if this is how it's working, but it's quite possible that one processor out of the number of cores I've got on my CPU is doing the streaming. The other one is running my Google Chrome at the moment, which is doing my slideshow. And there's another one that's doing, I don't know, maybe my audio processing or something like that, right? So we can split up these tasks, and the tasks can be very, very, very different from each other. And we can do sort of 8 of them at once. If we're trying to do more than 8 things at once, they get swapped in and out, and they get run in different times. So this is the rough idea of how fast this thing is doing. So The 3.6 gigahertz is how many individual instructions it's doing per second. And then you've got the 3090, which is a very, very different processor when you look at it from this perspective. Instead of 8 cores, so we think it's quite exciting that we can do 8 things at once with our CPU. Our GPU is doing over 10,000 separate things at the same time. So I say separate, but it's gonna come out that it's not actually separate, because every one of those cores is running another version of exactly the same code. It's not always the same, like you can compartmentalize these things, but the way we're going to think of it is really that we're running the same code at the same time. So the CPU is fast, and what we could think of as intelligent in a sense that it can do many different things, and it's really good at multitasking. Whereas the GPU is saying, I'm kind of good at multitasking in that I do many things at the same time, but they're all the same thing. It's interesting, right? And then the clock rate is also an order of magnitude slower than the CPU. So what we're doing is we're getting a processor that runs a really wide cycle instead of a narrow cycle quickly. And there's no reason to say that either of these is higher technology than the other. They've just grown into a specific purpose over time, over iterative development cycles. So the trick here is this number here, as I said, was about 2 million. Is it 2 million? 2,000, yeah, 1,000's a million. So about 2,000 by 1,000 pixels is about 2 million. Each one of those pixels, basically, most of the time, is going to require the same code to figure out what color it's supposed to be. So it's going to go through some stuff and decide based on the information I got from the CPU and what's going on in the GPU. It'll go through an entire process and it'll say, this is the color that I should be displaying in that pixel. So the more of these that we can do at once, the easier it is for us to go, here's a chunk of the screen. All right, we've done it. Here's another chunk of the screen. Okay, we've done that. Here's another chunk of the screen. We've done that. So doing them 10,000 at a time is usually more efficient than trying to do only 8 pixels at a time and then having to go so incredibly fast to get through all of those 2 million pixels. So that's, I'm hand waving here, but you get the idea of why this thing is a sort of a massively parallel processor rather than what is much more of a serial processor in the CPU. The other thing that's happening actually is that the CPU is a much more variable processor. It has many more things it can do than the GPU. The GPU has a much more limited instruction set. I like to, this is why I've got the subheading here, that the GPU is a massively parallel floating point calculator. Because nearly everything that the GPU is going to be doing is going to be working on floats. Actually floats a lot of the time rather than doubles. When you think about it, the color is your 24-bit. So if we end up... Actually, color's not the best example. Color's an integer. We'll talk about this later. We're going to be working 3D coordinate systems, and they're going to come out as these floating point vectors that we're going to be using. So we have 2 completely different ways of doing things, and I've also put a YouTube link in here. You can watch this later. I had a copyright strike on my channel when I played other YouTube videos. This is really short. It's only like 1.5 minutes long, but it's a really funny thing that was shown at an NVIDIA conference a few years back, and it's showing the difference between serial processing the way a CPU would do it and parallel processing the way a GPU would do it. Michael's asking me if we can copy paste the link. I can indeed. Okay, so that's the kind of difference between those two and some of the reasoning why they exist. But one interesting thing is that the rendering process that I'm going to talk about, the ability to decide what color each pixel is on the screen, can technically be done by the CPU. It would go at speeds that we would not find acceptable in the present day. But the CPU can do what the GPU does. It would just take longer to do it. Because what the GPU is doing is going through a series of algorithms that takes a virtual image and turns it into colors in pixels so that the humans can see that virtual image, that idea of something. The CPU is fully capable of doing that. Whereas if we had a GPU at the heart of our computer and no CPU, there'd be things that we wouldn't be able to do. Or maybe we could. I'm not sure. I'm not sure how much effort it would take to get a GPU to do all the standard processing stuff that we expect it to do. Again, might slow things down massively. Okay, not going to go too deep into this stuff. Got other stuff to talk about today. So, I want to talk about Polygon Rendering. I love how I have a slide with only one line in the title, and I'm cutting off the corner of it with my face. Anyway, you can still read those words. Polygon Rendering and Introduction. I'm wondering whether I should take a break now, because it's 10:55, and otherwise I'm going to take a break in the middle of the Polygon Rendering. So I was going to go to my break slide, but my break slide actually... Oh, you know what? No. I'm just going to talk about Polygon Rendering and we'll go for a break afterwards. So we're going to go for a break, not exactly in the middle of the lecture, but after I talk about this. Because this is a cool bit and I want to do it in one chunk. And my break slide follows from it. So anyway, here's a polygon. There's no image credit on this because I actually just made this in Google Slides. So polygon rendering is taking the concept of a scene, a virtual environment or something like that, and turning it into an image. And polygon rendering is a huge conceptual thing, and is a huge technique which we're going to teach you over the course of like 9 weeks, 10 weeks, right? So I can only give you an overview if I'm going to spend like 20 minutes on it now, but it's very, very important that we get this overview so that you have an understanding of where you're going to go with this. So we're going to start really, really simple. A polygon is a shape made up of vertices and edges. So this is a vertex, that's a vertex. Each of these things are edges between them. When this thing is contained and joined up together, we have the idea of a shape, of an individual object or something like that. I mean, when we're talking graphics, this thing would actually probably have been split up into just triangles. We tend to work on the simplest shapes we possibly can, most of the time triangles, sometimes quadrilaterals. So if we have an individual shape made up of vertices and edges, then we have the start of an image. If we go back to my last lecture, I was talking about asteroids. They just had this. They had edges and vertices. They didn't have anything else. We've advanced beyond that, and we have the capability of having these shapes have their own colors and things like that. But I'm jumping ahead of myself, so we're just going to go with the simple thing. Polygon's a shape made up of vertices and edges. If you start joining these things together, you can start creating complex objects. So some of you, this is the point where everyone's like, I know what that is. I know what that is. That's the teapot. Indeed, this is the teapot. One of the earliest things done in computer graphics was to create this teapot. It happens to have been a teapot that was at the University of Utah, and they modeled this teapot because it was an interesting use of the parametric equations that we're using to make curves at the time. It had enough complexity in it that they could really test how well their computers were dealing with this kind of polygon mesh graphics. So this teapot, super famous, and you will see it a lot in computer graphics. It's to the point where the OpenGL primitive objects are sphere, cylinder, cube covers all rectangular objects, and teapot. I think that's all. Oh no, there's got to be more than that. But I think that's pretty much it. And it's really funny that the teapot has been one of the primitive objects because it's just a nod to the historical idea that this was one of the earliest Hello World objects in graphics. So there's no way that I could do a computer graphics course without showing this teapot at some point. And it's nearly criminal that I didn't show it in the first lecture, but the first lecture wasn't necessarily about that. And also would have to explain what a mesh is by then. So a mesh is an interconnected set of vertices and edges that then ends up becoming a surface. So what we get is these vertices aren't just corners of one shape. This vertex here is the corner of 4 different polygons. So these ones are quads. Nowadays, we'd probably have a line through each of these quads to use them as triangles. But either way, we'll talk about all that stuff later. Even like thinking about whether something's a triangle or 2 triangles for a square, or a square or 2 triangles, not super relevant right now. But anyway, when these polygons share vertices, it means that they're right up against each other and there's no gaps in between them. And this creates an entire surface for something. So now what we get is the capability to show an object by saying that an object is defined by its visible surface. So most solid objects in the real world, the only parts of it that we can see are the outside surface. So when we're thinking about computer graphics, we do not even bother with what's inside the surface. We only bother with what's on the outside surface because we're only worried about how we can make this thing look visually. So if we have enough of these polygons in an object, they can piece together to show the rough shape of that object. And the shape is rough based on how many vertices and how many little polygons we have on the surface. So if we want a curved surface like this, you can see there's no curves on this teapot. Not a single one of these polygons is 3-dimensional. They're all 2-dimensional polygons. They're all dead flat. None of them have a curve in them. None of them are buckled or twisted or anything. The only thing that we have is that the polygons aren't all kind of like lined up. We can have 2 polygons that are dead flat, one in this direction, one in that direction, and it gives the implication of a curve. Again, nothing that we do in graphics is real. It's only the implication of it. So you can see around the edges of the top here, you can see it's kind of jagged. It's not a smooth, round top of the teapot. It is made that way by a series of flat lines. There's flat surfaces or straight lines, but each one is on a slightly different angle. And the only time it kind of changes direction is when they're kind of hitting a vertex at a different angle. So now we have the idea of a surface. We have the idea of the outermost layer of an object where we are completely ignoring the inner layers of the object, and people have already said that it's interesting that there is no bottom rendered on this teapot, and this really fits in with the whole graphics thing. Is we didn't have animation yet at this point, so the teapot was just sitting on another flat surface of other polygons, so no one ever bothered to model the bottom of this teapot, because if you can't see it, there's no point modeling it. And that, when we get into optimizing graphics, that's just going to be like this massive thing. If you can't see it, don't render it, you know, and that's actually going to be like a significant portion of how we optimize graphics to run fast on things. So what we've got is, at the primitive level, vertices, edges between the vertices. If you have enough edges so that the edges go all the way around in a loop and they return back to the same vertex, then you have a shape, you have an individual polygon. Putting all these polygons together at different angles in 3D space is going to give us a mesh and an object. Now, we're going to be in the course working just with a flat 2D space first, getting a good idea of what we're doing, and then converting things into this 3D world. So we'll get there. I mean, we're going to get there pretty quickly, but we'll get there. So what I'm giving you now is a big overview of things, not necessarily the order that we're going to be doing them. Actually, it is the order, but I'm jumping to 3D pretty quickly. So how do we keep track of our vertices? We keep track of our vertices by putting them in a coordinate system. So if we were to say every vertex on this teapot exists somewhere in a 3D space, so a three-dimensional space, the easiest way for us to say where points are in a three-dimensional space is to say what are their coordinates. And so we can have an X and a Y and a Z. Looking at this, I don't like this coordinate system at the moment. I would have preferred if we had the Y going up, and the X going across, and the Z being the depth. But anyway, this is an example of an XYZ coordinate system. We're much more often going to have the X going from left to right, on your screen, left to right. I'm just looking at what my OBS is saying. The Y going up and down, and the Z coming towards you out of the screen. But anyway, not super important. That's just a fiddly little thing. Either way, the idea that every vertex has a set of coordinates that exists in space is something that's important. So this is just going to be a group of 3 floating point numbers, which is a vector. And I'm saying this as a vector, not a programming vector, which is like an expandable array, but I'm talking about this as a mathematical vector, which is a series of numbers that are related to each other. So what we're reaching now is we are bridging the gap between image and data structure. So now what we're saying is we can bring this into a computing context. If we have 3, it's actually 4, but we'll get into that later, floating point numbers to represent a position in space, suddenly we're back in a world we 100% understand with programs. Like, oh, this is just a bunch of numbers. I can crunch numbers all day. That's all I've been doing. And all my other programming is like, we crunch numbers in a particular way, different set of numbers come out. This is amazing. That's like all of computing. It's like, we feed in numbers and other numbers come out, and now we take over the world. Right? Just everything in computing. Graphics is no different from everything in computing. We feed numbers into the graphics card, we fiddle around with those numbers, we get numbers back out which tell us what colors should be on the monitor, we trick everyone into believing they can see something, voila, we're done. Right? That's all it is. We're just moving numbers around. Entire field of computing. So, let's say this 10 times fast. Vectors of vertices. Vectors of vertices, vectors of vertices. Actually did all right there. Anyway, the vertices are numbers, usually floating point numbers. I mean, it's very hard to do things if they're not. And they're in vectors of 3 numbers. It's actually going to be 4 when we're in 3D, but we'll get into that later. There's a 4th number for doing magic stuff. But these coordinate systems allow us to know where in a 3D space everything is. But on top of that, they bring us into a world where we have all of this ready-made tech for us to use for moving these things around and transforming them. So you may have heard of transform matrices in linear algebra. If anyone's done, I don't know what it would be called now. Is it Math 1B? Do people still have Math 1A and 1B? I don't know if I'm like my information on maths is very old. I should just call Dan Mansfield and he will tell me that something about Babylonians. I'm allowed to make fun of him, he's my friend. But yeah, knowing that we can then apply matrices to these vectors of positions means we can move them around in this space. But we're not just moving them around willy-nilly. If we apply certain matrices to these things, I can take this entire teapot and shrink it, or grow it, or rotate it and stuff, knowing that I can apply that to all of the points on the teapot, all of the vertices in a consistent way so that they end up in the right position, in the right shape. We can even get to the point where I can transform the objects in the scene into an idea of what should be shown on a screen. So this is a image credit, high level, international award winning artist here. This is what this is what I came up with for how we look at a virtual scene. So I've actually done my XYZ coordinates in what I would consider a more graphics correct way here. I wanted to find images online for this, but I couldn't find anything that worked for me, so you're stuck with my brilliant art. Okay, so on the one hand, we've talked about this already. The monitor displays an image to the human. The human's perspective on that image is from our eyes to the pixels. So our eyes to the pixels look at our monitor, but we're not looking at the monitor like it's a flat surface of monitor. We're looking at the monitor like it's a window into a virtual world. So like we're sitting in our room and the monitor is the window to the outside, right? But it's not the real outside, it's the virtual outside, which is something like this virtual world here. And I've kept this quite simple. So there's a virtual camera in this world that's looking out at the world, and it's trying to show us the same perspective that we would see if we're looking at it, looking at our screen. So there is this virtual idea of a screen. There is an idea. It's not really, it doesn't exist necessarily. I mean, it kind of does, but there's the amount of stuff that is able to be seen in this virtual world by this virtual camera. So we always draw this picture of a camera in the scene, but it doesn't exist. It's a theoretical single point in the coordinate system that we're looking at. But what we can do is we can apply linear algebra, transform matrices to figure out which of these objects and how much of them is actually visible from this perspective. So we look into our virtual scene from the perspective of our virtual camera, and we go, all right, I'm doing this rough, right? But we can see part of this circle and part of this cube here. So my viewpoint from here is able to see those things. And so that's what ends up happening on those pixels, and it goes to the screen here, and then we see it. If there's only one image that is the entirety of Polygon Rendering, is this image. So this, I mean, the circle, I probably needed to draw a lot of little lines on that to make it out of polygons, because a sphere or a circle actually needs a lot of little vertices around it to do the curve. But I didn't bother doing that. I just wanted you to see the concept of, like, if these things are appearing here, this is what this camera could see from that perspective. So we would then go through each of these pixels and go, what color are each of these pixels? And there's some blue ones and some orange ones and some white ones, and that's what appears on our monitor. The way we get there is by having a mathematical system for all of the points and in this coordinate system, and knowing that we can use linear algebra to transform the positions of all these points and all these objects into something that we can see. So what we're kind of doing is, like, we're taking this virtual world and this virtual camera, and we're just like rotating the whole thing around in such a way so that it lines up in a way the way the camera would see it. And then we look at that and we put those on the monitor. Another way that we can look at it, if we want to, is we can take this virtual camera and we can look through each of the pixels in this idea of a screen. So we've got this idea of a screen in our virtual world. So that one definitely doesn't exist because the screen's here in the physical world. And we look through the pixel in the top left corner. And then we can look through that pixel in the top left corner and basically extend a mathematical vector, like a direction into space, until it hits something. And then when it hits something, we go, that's the thing that we can see. And we go, what color is that thing? And then we'll put that on the screen. That's not exactly what we're doing, but it's a nice way to think about it conceptually. And we do that for every pixel. So for every pixel we look through, we see what it can see, and we pick up the color from what it can see and put that on the pixel on the screen. And so we go through each one at a time, and then that is how we end up with this big two-dimensional array of pixels, as I said. So everything we're doing today is building up to this, in a sense. So here's the text for what I was just saying, but I wanted to stay on the image. So if every pixel that was on our screen was actually in the real world, and we drew a line through that pixel, that's the idea. this is I don't think I need to actually talk about this slide, I think, because this slide is again just in text what I've been talking about. I do write my slides so that if someone doesn't happen to read the to listen to the lecture, or they go back to the slides afterwards, you can kind of remember everything I said. But I think I've said all of this when I was looking at this image, because I think this image is the important thing to see. But let me just check to make sure. Yeah, we're mapping 3D coordinates onto our 2D monitor. So that's from a mathematical perspective. It's good to think about that. So we've got like, this is actually from Learn OpenGL, which is the textbook. It's a web page, but textbook. It's a book as well, but anyway. The virtual camera is in the virtual world, so it has coordinates. And when we get deeper into it, we also know that the virtual camera has a direction that it's looking. So it's looking somewhere in the world, and it has an alignment in terms of like how it's rotated when it's looking in that direction. So we got a lot of details about the camera. And with all those details, we can mathematically determine what everything should look like if we just rotated it all into the perspective of the way the camera is looking. So, yes, this is my I don't have time to teach you all of this right now. We are going to spend time on this, is we can tell what the camera should see using maths. Again, today's an overview. This entire process is huge, as you can tell. Like, you're looking at this and I'm just like, wow, Mark is making some big jumps here. How did we get from this to this? How do we get from this to this? You know, big jumps. All right, so let's accept those, because what I'm giving you is an overview of the entire process. And then we spend weeks and weeks and weeks getting into the nitty gritty and learning how to do that process. Okay, time for a break. I think this is a good time for a break anyway. So 5-minute break. And everyone was like, oh my God, we had a Mark Chi lecture and there were no memes in it. So here is the first meme of 3421. 9415 also. I should stop calling it anything by numbers, because this course has 2 different numbers. So I'm just going to call it computer graphics. So, as I say, graphics can be excessively technical and involve a lot of maths. But I want to tell you my perspective on this highly complex mathematics that we're using, is that we're going to use it without needing to know it in extreme detail. I'm still going to assume that you know it even if you've forgotten it. You know what I mean? So if you've done linear algebra and maths, got through your exam and promptly thrown it all away so that you can remember the lyrics to the latest BTS song. Look, it happens to me as well. Or the exact order of what Rick Astley won't do when he's rickrolling you. That stuff stays in your memory forever. But linear algebra, I understand most of it probably hasn't stuck in a lot of people's heads. That's fine. We can use it without knowing every detail. That is, in a sense, the point of a lot of computing, is to say that if we did everything by hand, we would never get there. There is no possible way that if we tried to do graphics by hand, that would go 60 frames a second. Like, think about how many hours it takes to make a film, for example. And a film has a set number of frames. Like, it has a set number of frames it needs to render, and then that's it. It's over. Still takes years to do 2 hours of film, you know? And even the computers are not going in real time in films. It's a standard, I think, 8 minutes per frame for rendering. So, like, every single still image in, say, Avengers Endgame or in any of those Marvel movies has a CG budget behind it of like 8 minutes worth of render time. And 8 minutes worth of render time for the frame is usually several hours of human work before that to make the art assets and decide what was being rendered. But anyway, we're going to use stuff without knowing it 100%. But we still want to understand it, right? We're not just going to use stuff without understanding it, because then we're blindly using things we don't know what they're going to do. So this is where we balance where it is. And so I just thought this would be really funny. It's just like bus bandwidth, coordinate geometry, linear algebra, all this kind of stuff. But you need this, or else this doesn't happen. Okay, let's take a 5-minute break. It is 11:18 now. We will come back at 11:23, and I will go through some of the course infrastructure and stuff like that. I've actually got stuff set up on my computer. I can show you a little bit of the dev environment. Not going to go in huge detail. But I think that's a good enough. I will have enough time after break to do that. So, be back soon. I'm enjoying the live chat there. I don't read the live chat when I'm in flow in the lectures. My focus is over here on the slides so that I can tell you things. But like in the break, I can look back a bit on the chat and people are talking about how maybe I shouldn't have revealed all of this before the censor state. And Mark's not drinking water; he's drinking the tears of his students. Um, but I think it's important, right? Because we go, oh, I want to make cool stuff, and you go, well, how do you make cool stuff? You you learn how to make stuff, which is very, very complex. And the idea that we're going to simulate vision in a computer, and the building blocks of a computer is a series of zeros and ones, and how do you simulate vision through that? It's complicated, super complicated. But I've given you an in. I've told you the entire process. Now it's a matter of breaking down that process into its individual parts and figuring out how each of those work. Again, that's what the course is. We'll get there. So, now that I have given you a conceptual idea of how we go from mathematical concept of objects, and I've given you everything you need if you want to be like, oh, hang on, where are we? Like, we can go from shape that doesn't make any sense to object that makes sense. Like, I didn't have to say teapot for people to look at that and go, oh, teapot, you know. So we can take this and it makes sense. And I've told you roughly everything that we can do to take this to the screen. I have not told you exactly the techniques or anything like that yet, but it's actually technically possible, so that like you could figure this out now. You could take a lot of Googling and stuff like that, but you could actually get each of these parts working. Maybe not to the monitor itself. The nitty-gritty low-level coding to actually get that to the monitor is something that we will work on. But again, that's why that's the next thing in this lecture. You now know the concepts that we use for turning three-dimensional objects into a series of flat planes and also getting them to a screen. So we've got enough background here so that the majority of what we're going to do in at least the first half of the course is not going to be a surprise. I left out huge chunks, by the way. The entire second half of the course is how we simulate light in this environment. I didn't show that at all. I will probably show that the entire idea of lighting in the first lecture after the midterm break, the week 6 midterm break. So we'll get to that. So I did leave some stuff out that's actually very, very important, but it's only important in terms of realism. It's not important in terms of getting stuff done, which is what I was just showing here. Okay, so coding graphics. How are we actually going to take the things that we know as, you know, computer programs? We're looking at like text input and output and stuff. Some people may have done some more advanced stuff with GUIs and stuff like that. But a GUI is not a 3D world. A GUI is not a virtual environment with like physical looking objects that can move around and stuff like that. You know, it's a very abstract world designed to treat the computer screen like it is a flat surface. You know, it doesn't have an immense amount of depth with like a horizon in the background and all this kind of stuff, right? So it's a very, very different way of doing things. So what kind of setup are we going to use to code graphics? So first thing, OpenGL. The question is, what is OpenGL? So OpenGL is known as, like, I don't think anyone even calls it this anymore, but technically, I think at the beginning it was the Open Graphics Library. Whether it actually is a library or not, I think is a point of contention. I have a feeling that you would not call OpenGL a library, but you'd call it an API. I'm baiting Simon here because I know that he's gonna have the technical, like the exact precise technical thing. I tend to just think of it as either one and just use it, you know. So the trick behind OpenGL is not the only thing of its kind. We could potentially look at something like DirectX. We could also look at a very much newer one than the other two called Vulkan. I would say that when we're looking at how much things are being used in the game industry, so these are actually the ones that are being used more in games. Film tends to have very, very custom things. Film has super, super specific custom things, and it's unlikely to be exactly something from one of these libraries. Yeah, good answer, Simon. In quotes, framework. Yeah, that's why I was just like, I don't want to call this an API or a library. Yeah. That's it. That noise is my response to trying to fit OpenGL very well into exactly what we expect of coding environments, in a sense. But anyway, let's talk about what it does. It gives us access to the graphics card. Yeah, PK Beam said was like DirectX on Linux. That's the reason why we're not doing DirectX, right? OpenGL is the one that's actually happy to go across multiple operating systems. Vulkan was always an option, but it's a little bit more fiddly. I've done so little stuff in Vulkan. It would have been like, if we're gonna do Vulkan, I don't think I can teach this subject. I'm just gonna have to walk away, right? So OpenGL is where we're at the moment, which is fine because I think it's a good one to learn. Really, we only had this choice because we wanted to work on multiple operating systems and be reasonably easy to learn. Out of the three, it's the one we go for. Anyway, what it actually does is it gives us access to the graphics card. Through OpenGL, we can have a system that allows us to bridge the gap between the CPU and the graphics card. So I was talking before, separate processors. And there are specific points where we cross over between one and the next. So when we're here and we have these objects that exist in this virtual world here, so this coordinate space, these objects we might well be doing a lot of stuff on our CPU with. We might well be saying this is exactly where these objects are, and our CPU is handling things like human input. So mouse and keyboard input. Mouse and keyboard input might be moving this camera around, might be changing what its coordinates are, and so all of that stuff might be happening on the CPU. And then at some point we cross over to the GPU and we say, all right, GPU, we know that you're very good at linear algebra. We know that you're very good at floating point mathematics. If I tell you where this camera is, and I tell you all the vertices for where these objects are, can you do the conversion into this screen space? And the GPU says, yeah, totally fine. It's what I do, you know? And so the amount of information that we're sending between the GPU and the CPU might not have to be that much. Because this camera, I don't need every single pixel. All I do is I've got a series of coordinates, a series of vector coordinates and directions, because vectors are directions that are used. You use coordinates to make directions. We'll go into the maths in more detail later. But yeah, I can send through a series of numbers, and that's all I need to send through to the GPU for it to know exactly where this camera is, where it's aiming, and what it can see. You know, and then I send through vertex information for these two objects. Now, the vertex information can get really hefty. You know, if you look at current game models, there's so many verts and so many triangles in current game models that maybe we do need a fair bit of bandwidth for that kind of thing, but we can handle that anyway. It's still better than trying to give all kind of surface data through to the GPU. So stuff is then processed on the GPU, and the system that we use to do that is OpenGL. OpenGL also is happy to hide a lot of stuff for us, like any API, right? So this is where it acts a bit like a API/library. I love how it's just like, I don't know which one it is, so I'm just gonna say API/library. We ask it to do things and it does stuff for us, right? So we don't know exactly how it's doing certain things, but we're just gonna let it do those things, right? So we can say to it, this is my camera location. Can you just make it turn those things into pixels? And so it's not that simple. We need to give it more information than that. But we don't have to do super low level programming. So if anyone's been working in assembler or anything like, I remember there was like an assembler fan last lecture, I think, was it? Or was it on the Discord or something? And it's like, no, we're not going to get to that level. But we will be doing some programming on the graphics card itself. So there is some code that actually goes to the graphics card, gets copied over to the graphics card, and it runs on the graphics card itself. So it's code that runs in that massively parallel environment that I talked about earlier today. That is shaders. So as opposed to the C++ that we're running on our CPU, the C++ is the thing connecting to OpenGL. We can then send stuff to OpenGL, which is in another language called GLSL, which is OpenGL shader language. I'm pretty sure. I don't know. Those of you who have learned from me before will notice that I have a healthy disrespect for specific jargon. So if you understand how something works and you understand that GLSL is the shader language, you don't necessarily need to know exactly what it is. I'm waiting for Simon, the human encyclopedia, to tell me if my acronym is incorrect here, but I'm pretty sure that's what it is. So C++ and other languages like it run on the CPU. And you know, all right, because you're third-year programmers by this point, you know that this dot point is just a massive oversimplification of the world of programming. But I don't mind. It's not that important, right? Because this is the way we're going to think about it. C++ runs on the CPU. shader language runs on the GPU. So we're actually going to copy this code onto the GPU and say, GPU, run this code. And it's really, really specific because the GPU is doing very, very specific jobs. It is actually, and we're going to go into this later. I wanted to actually put this in this lecture, and I was like, no, Mark, don't try to squeeze like 15 hours of content into one lecture. You've already done too much. So I'm going to talk about this, but the entire process of what the GPU does, I'm going to go through later. It's called like the OpenGL pipeline, basically, or the rendering pipeline. But these shaders are going to do these things. So there's what we call the vertex shader, which is one code program written in GLSL. And there's also the fragment shader, which is a separate program running in GLSL that runs on your GPU. These will be run basically sequentially. They'll go one after the other, where I am kind of hand waving over this stuff. We're going to go in detail where the vertex shader runs once per vertex. So every point on that teapot, so every corner of every polygon on that teapot will have the vertex shader code run on it. And the vertex shader code is going to do things like manipulate these vertices in a sense. So it's mostly not going to be changing them or anything, but it's usually going to be pulling information from these vertices and saying, all right, given what we're trying to do, we're trying to put information on the screen, these vertices are going to come with more information than just their location. They're often going to come with information like what color is the object at that point in the object. And that can be based on the sort of fundamental properties of the object, but can also be based on things like how's the light hitting that object at that point in time? Is there a particular surface that object should be simulating, and what does it do? And these things will tell us what color might be there at that particular vertex. I'm glossing over a lot of the details. Again, we've got 9 more weeks to go over those details, and we will be doing so. I'll actually show you some of this today because I've got the code set up. I'll show you in a second when we're talking about code. And then the fragment shader that runs, probably shouldn't have said this. It kind of runs once per pixel. I mean, for the moment, just think of it like it runs once per pixel. And what it'll do is it'll go through all the pixels on the screen and will pull information that the vertex shader has created for us. So very, very often, the vertex shader will send information to the fragment shader about the vertices on screen. And the fragment shader will go, okay, based on the vertices that this pixel fragment, it is technically fragment, not pixel, but you know, it will basically be running once per pixel. And what it's going to do is it's going to say, what color should this pixel be? Based on the vertices near where it can see, and this is a more complicated thing of like, if this pixel sees a certain object, and then that point on that object will be somewhere between the vertices of that object. It's very rare that the fragment hits the vertex directly, so it's in between the vertices, and so it says, okay, I take information from the vertices around it, and from that I can tell what color this pixel should be. So information from the vertex shader that gets passed into the fragment shader. We can show some simple examples of this actually, and I will in a moment. I think I've got it. Yeah, okay. I'm going to talk about that later, but I've got the coding set up. Anyway, so we're going to be using C++ in this course, and I did say this last lecture, but I'll repeat it here, that we're using a specific subset of C++. So we're not using all of C++ because we didn't want to necessarily make it so that you needed to have studied C++ before starting this course, but we do need some of it for it to work. So we needed you to be able to get involved quickly and start doing graphics, not doing C++. But we also needed certain features to exist for us to actually be able to do graphics at all. If you want to know, we have a video primer on the specific C++ features that we're using. So anyone that's familiar with just programming in C, hopefully this primer and reference project that we've made is enough. That will get you using the basics. And if not, I do have the assumption that everyone who's in this course has done probably more than one language. So If you're in UNSW, you've done COMP1511, which means you've done C. If you've done any of the courses following COMP1511, except for, which one is it, 2521, then you've seen another language. So you've already experienced the jump from one language to another, which I think is one of the most fundamentally important things for beginner programmers to do. To be able to say, I can program in 2 languages. Because if I can program in 1 language, then I only know I can program in 1 language. If I can program in 2 languages, I have shown that I can convert my knowledge of programming in general, and the languages are no longer holding me back. You know, so I could say that every language is holding you back because every language is limited in some way or another, you know. And if every language is limited, you will see when you cross from one language to the other what is programming and what is coding in a language, right? Because the coding in the language is the limited thing. The programming is what's in your mind and your capability to get computers to do cool things. Right, and that's the important thing, obviously, and then you can translate that into any language if you've got enough information around you. So what we're hoping is we've given you enough information so that you'll be able to use this. Yeah, so we're using C++. We've got some help here to get you set up. We have a specific code set up as well. So this is the code setup that gets us cross-platform capability while still having, so you can use whatever computer you have. Well, not whatever computer, it's basically recent versions of Windows, Linux, and Mac OS. Like, we can't support everything. But this is quite a wide breadth and should cover the majority of computers that people are using at the moment. And if anyone's using something super weird and different from these, then I assume that you're good enough with operating systems to run one of these as another boot on your computer or as a virtual machine or something like that. Graphics support on virtual machines is variable though, so I'd be careful on those. Anyway, so we did it with CMake, which works with different operating systems. I actually just yesterday put up a new video from Kaichi. I think Simon's in it as well, right? Which helps people getting set up with CMake, or even just an understanding of what CMake is. So CMake is a build system, and it's, what would I call it? A platform agnostic build system that works very well with C++, and it means that you can get a set up in multiple languages and work. It's not IDE specific, but amongst the tutors, Clion, Sea Lion, I don't know how to pronounce it. I've never actually used it before. And VS Code are reasonably recommended. Visual Studio works as well. And people were saying earlier in chat that someone had Visual Studio running without installing anything for CMake. So that means that Visual Studio is now coming packaged with CMake support, so that it's that it works without a separate CMake install. You also don't need to buy an RTX 3090 to learn how to code graphics. This is hilarious. This got in here based on chats on our Discord about it. People were like, Mark, will you buy me a 3090? And it's like, no, of course I will not do that. I didn't buy myself a 3090. You will be able to do everything in this course. I reckon you can do everything in this course with an integrated GPU on an Intel chip. Depending on how well or how badly you code things, this thing, it might slow down in terms of frame rate. When you think about it, like the games that we play have vastly more complex code than we could learn to write in 9 weeks. However, even with the vastly more complex code, they're very, very much better optimized than we can learn to do in 9 weeks. So if you are running integrated graphics, or you're running a 3090, you could blow it up with this course just by writing really bad code. Like, you can do that. Like, I can use up all my memory with 5 lines of code if I want to. You know, it doesn't mean it's the right thing to do. So, but what I'm saying is you don't need super high hardware requirements. If you want to get help setting up, we've got this GitLab project with a whole bunch of instructions in it. I think, did I? Might be here. These are all linked from the course webpage. as well. So let me jump across to this and show some of this to you. So this is me. Too small for you to read. Wait, can I zoom? I have not used VS Code very much. Appearance? Zoom in. Oh, control equals is zoom in. Oh, right. It's because it's plus. I was doing control mouse wheel. All right. Hopefully you can see that reasonably clearly at the moment. Actually, looking at my OBS screen, maybe I need to make that even bigger. Put that aside. Move the terminal down a bit. I forget. Sometimes I go back and forth between, you know, broadcasting coding and coding for myself. And then coding for myself, obviously the font is much, much smaller. Michael's like, please zoom in. Yes, there you go. I'm zoomed in now. Hopefully you can read that a little bit better. I've spent years in Visual Studio, but then I figured that since so many of my students were using VS Code, that I would learn how to use it. I haven't used C-Line either, but I'll check it out in the future. I mean, it'll go on a list of things that I'm going to do in the future, along with all of the movies and games that I want to watch and play, and I will get to some of them before I die. That's the only promise I can make. I think a lot of us are in that same position. Okay, so this setup, I did it in Windows with VS Code, installing everything in... Oh, wait. I just need to press the view in browser button. What I did, and I did this specifically because I kind of wanted to test it as well, is I just followed the Windows instructions that Xavier, one of the tutors, put together here, and I just did it blindly. Like I just the MSys2 terminal and just copy pasted each of these things in here. It was about half an hour, and I went from half an hour from having nothing. So I had literally, at that point in time, I made sure I had nothing on my computer. So I had no VS Code or anything. So I installed everything from scratch. And it was half an hour from nothing to OpenGL window opening. So I was pretty happy with that. So big up to Xavier. But I mean, like, I say big up to Xavier. It worked for me. I know that it's not 100% working for everyone, but we'll help you through that stuff. So potentially the first tutorial might help some people with stuff, but I mean, we're obviously going to teach content in the tutorials as well. We also have our Discord and our Ed for help. So if you will like ask big questions, you can go on Ed. We'll potentially have some time for tutors to help students with debugging setup issues, because I do understand that this is slightly more than setup that we may have for certain courses in CSE. But again, this level of instructions and setup is way better documented than a lot of the random things that I've had to set up as in life as a software engineer, you know. So hopefully, if it doesn't work first go, you can figure out what to do with it and then get it going. One could nearly say that this is a test, and one could nearly say that a significant portion of the marks in the first assignment are assigned to whether you can get through this process and get it working. There's a reason why I have the first assignment like that before the census date, so that you get a chance to actually figure out how... Sorry, I should have like zoomed this in, but I'm not reading it right now anyway. Yeah, getting your own setup going, getting your IDE going and stuff like that is something that I would consider I don't know if I'd say it's a core skill of a computer scientist, because there's plenty of computer scientists that work in different ways. But in terms of a graphics programmer, I would say, yeah, this is a core skill that is necessary. You got to be able to make your own setup and get it going. You know, for someone who's doing kind of abstract knowledge representation AI or something, and it could be like, this is not important. Where's your whiteboard? You know, so it's a different thing, but I consider this core to be able to do this kind of stuff if you want to be a graphics programmer. So anyway, but instructions are there, and you can get that stuff going. So half an hour of work. I get to this point. Oh, David was asking what VS Code extension do you have installed for vert and frag? Let me. Yeah, because this is something I did which wasn't in the I love it. I can't navigate menus while I'm talking because too many words are hitting me in the face. I can't remember which extension I installed, so let's go check extensions. I found this one called Shader Languages Support for VS Code. It was actually really funny because it was I opened the project and VS Code did a pop-up at the bottom saying, hey, we see you have .vert and .frag in your files. Would you like an extension to be able to deal with those? And I was like, yep, and just clicked on one of them. So I didn't think about that much, but all I needed was to get some syntax highlighting going, and that's it. Okay, so if we go through, I just did Hello Triangle here, which is like one of the demo programs that comes with this setup when you build it the first time. So we've got some what we're calling resource files, which is the two shaders. When you look at GLSL, it should be quite whatchamacallit, it should be quite easy for you to read, because when you see this looks like many other languages, so it's obviously a C derivative language. But the key elements of it are going to you're going to learn about eventually, like what is layout and stuff like that. And then here, what is out? I mean, you can probably guess that out is an output. One of the most important things for the fragment shader is this thing called frag color, basically, which is like, what color should the fragment be? The last thing the fragment shader is supposed to do is to basically say, this is what color that thing should be. So we've got our C++ files, and we've got a lot of helper stuff here, which is basically going to be part of every project that we give you, so that you don't necessarily have to do this stuff yourself. Stuff like, here is some code that grabs these files and passes it to the GPU, so the GPU knows to use the shader files that we've got. Not going to go too deep into this stuff because this is what the tutorial is for, but I realized that I have just enough time in the lecture to do a couple of minutes of this, so I thought I'd show you. Michael has noticed the American spelling, and I said, is it in here? Get used to this. We in Australia spell color with a U in it, and every time I do something like this and my graphics code doesn't work, I have to keep remembering that there are keywords in every programming language that we use. So keyword like void is in most programming languages that we use. Keywords like int and float and double and stuff like that. It just turns out that when you're doing graphics programming, color is a keyword in graphics programming, and it is a keyword in GLSL. It's a keyword in OpenGL as well, well, as parts of other things. So if we spell it Australian, the code will not work, right? So get used to reprogramming your own mind to do all of your graphics programming in American. Because if you don't, I mean, we do it all. I do it all the time. I spell color incorrectly for OpenGL, correctly for the way I learnt Australian English. But, you know, we're going to make those mistakes. You'll find out soon when this doesn't work. Then you'll notice. So this example has something pretty simple. I haven't actually looked that close at it, but it's got a window that's being made and all of this OpenGL stuff. So we're actually using this thing called GLFW, which initially was an acronym for GL for Windows, but it actually works in other operating systems, obviously, because it's working in Linux for people who are using it. And this is going to do stuff like set up the window and stuff like that. And I think we have here a vector of vertices that is going to be our defined object that we're going to pass through the graphics card and say there's these things. So we have, I think this is color information, positions or colors. I'm not sure which. It looks like these are positions though, just looking at the coordinates. So we've got like a X coordinate, a Y coordinate, and a Z coordinate. So the Z coordinates for the 3 vertices here are all 0. So we're working in a flat plane. We're not doing anything going towards or away from us. And we've got one point that's just up, one point that's up and left, and another point that is left and down. I think if the X, Y, and Z are in that order. Yeah, and so we're making a mesh out of these vertices. And I'm not going to explain all the code here. I'm going to let the tutors explain the code. But what we're basically getting is 3 verts. And our background color is 0.2, 0.3, 0.3, which means it's going to be a teal kind of color, a bluey green background. So if I run this, hopefully this is actually built and ready to go. I can't remember what I was doing with this last time. What I'm getting is a triangle. It happens to be a red triangle here with that teal kind of background that I'll show you. Oh, don't worry about this stuff here. That's just my gamer add-ons detecting that I'm running OpenGL, which is a good sign, having this saying, yes, we are actually running stuff on the graphics card, and this is giving me my stats on whether my graphics card's doing things or not. So the vertex information has gone through and said these are the positions of the vertexes, and the color has come from somewhere. So we can actually have a look at where the color is coming from by having a look at these shaders. And I'm pretty sure the fragment shader, I had a look at this earlier, right? The fragment shader is saying, I'm just going to tell you what color this thing is going to be. I think the tutors are probably going to go through this stuff, but I can fiddle with this if I want to, and I can give different color information. So assuming that this is red, this is green, and this is blue, the reason why that triangle is red is we have a full value of 1 in the red and 0 in the green and blue. So if I want to make this thing yellow, I will mix red and green together. Trust me, that actually is the truth of how those colors mix together. The funny thing is, if you take red and green paint and you smush it together, you're highly unlikely to get yellow. But this is what happens when the rods and cones in our eyes are activated equally with red and green. It's weird, right? It's not exactly real, but it does work. So I build this again. I think this works. I remember though there was some fiddly stuff with VS Code where we might have to close the terminal and reopen it to get this to do the new build, but let's see what happens. Oh no, it's fine. It's not that fiddly. So I changed the color here in the fragment. I have a different color on the output there. So I don't want to go into too much detail because the tutors are going to teach you this stuff, but I wanted to show you at least this is the setup that we've got going so far. There's a lot of code here that you don't have to understand yet. You know, we're going to get through it. That's why I was glossing over it and just jumping in for where the numbers were. Oh, I could change the background color if I wanted. Oh, let's not. We're pretty much out of time. But this is the environment that we're going to be working in. A lot of these things that give us access to OpenGL things, we've got a lot of this code for you. So we didn't want to have to spend like the first 3 weeks teaching you how to do configuration stuff for low-level OpenGL. Like, that's the kind of thing which is like, yeah, sure, it's a good exercise in that. And if you want to, you can start from scratch and you can delete all of these files. Don't do it in the project you're going to use for tutorials or anything like that, but you could start a separate project, delete all those files and learn how to make all of the GL calls and stuff like that. But it's not it's not like 100% vital to understanding and working with graphics. It's the kind of thing where everyone does it once, in the same way that, like, it's not really the same, but like, let's say for example, I ride a lot of bicycles, and once I built a bicycle entirely from parts. So I learnt how to, like, grease the bearings and install them and install the handlebars in a way that's not going to fall off and kill me and all this kind of stuff, right? So just once I did that, but it's not necessary in terms of like knowing how to ride a bike to be able to build it from the ground up. So this is why we've got some of this stuff for you, which should help with some of those things. All right, we are at the end of the lecture. I must wrap it up there. Oh, someone was asking about what the fourth thing in the color is. Yes, it's the alpha channel. It is whether something is transparent or not. We're not going to go into that yet. Transparency causes massive issues in rendering, so let's not even get there yet. We'll talk about it eventually. Okay, so what did we learn today? We went through the graphics hardware. So we went through monitors and how they work and how they're all an elaborate trick that makes humans believe things, but it works, so we use it. And graphics cards, a little bit of the rationale why they exist, but more on the difference between them and CPUs and why they do the job they do. And then we looked at polygon rendering, which is an overview of the process from this kind of abstract mechanical mathematical concept of shapes, vertices, and edges and stuff. And I hand waved over a lot of this because, again, we're out of time now, obviously. Then how we eventually take that to what color the pixels should be based on this mathematical transition from those flat shapes to how do we tell what we can see, and then what do we put on the screen. And then we looked at how we're going to develop stuff in the course, and an overview of OpenGL, shaders, the C++ we're going to use in the CMake project, and a little look at that project. I didn't really do much in that project, but at least you can see how you could play around with that if you want to, and do stuff with it. Okay, we're going to wrap it up there. Some of your tutorials are happening in barely hours, I think. I think it's 2 hours from now is the first tutorial. So what I'm going to do is I will go into break mode to cap this off, as like that's the end of the lecture, and I'll hop back in and answer some questions if people have questions. Looks like people have already got some questions there. But the answer to a lot of your questions is we will cover it. You know, like what the intention for today was to give everyone a solid idea of the overview of the process, so that when we go into the nitty-gritty of the process, you go, oh, this fits into my worldview of what graphics should be doing, right? So I feel like I need that overview. I feel like if you don't have context for why you're doing matrix mathematics, you'd be like, why are we even doing this, right? So you'll get there. Okay, so thank you for coming along. And we will, and I'll come back in a second and answer any little questions anyone has. Otherwise, have fun in your first tutorials. And if anyone's having any issues with getting the coding environment set up, your tutor is probably a good person to ping in the tutorials. What I'm going to do also is like talk to my tutors afterwards and find out how many people had issues, and we know, like, then we can get a statistical idea of how good our instructions are and stuff, and then we'll help everyone out if you can't get stuff set up. All right. See you next week on Monday. I probably won't see you between now and then. I'll be on the Discord every now and then and say hi and stuff like that. But otherwise, see you next Monday, and hope your first tutorial is fun. See you later. I'm back for little questions. Oh, thank you everyone who is saying thank you. That's very nice. Hexus1 said, do I have to speedrun the setup before the tutorial starts? You don't have to speedrun it, but I would do it. But you don't necessarily have to do it, but if it doesn't work and you do it after the tutorial, then you've missed a chance to just kind of like ask your tutor. It's like, hey, did I do something weird here? And the answer is like, maybe, you know. So, and I was saying it took me half an hour. So I actually think it's worth it. And everyone has time before their tutorial to do that. Or at least to have done it the first time and see that it doesn't work, and then try to figure out where you got up to or what questions you're going to ask. So this is something that's like universal in computing tech support and stuff, right? Is, can you ask the correct questions to get a good response? So for example, when I have problems with something technical, I can say, I have done these steps in the process. Everything was successful up until this point. When I ran something, this particular thing happened. I actually pinged Xavier with something. And I said, hey, I got to this point and this part of the code wasn't running. And it's like, yeah, that's a weird visual, like VS Code thing. And I was like, don't tell me. And I turned it off and on again and it started working. And I was like, okay, fine. The rule of anytime you make weird changes to a system, you just turn the whole thing off and on again, and then everything just settles into place. And I was like, oh my god, why does that rule still work? Can we not have gone past this at some point, you know? But now my VS Code's fine, and you saw me there change my shader, rebuild and rerun it, and it was totally fine. But it was so funny that the first time I tried to run it, it was because I hadn't done the startup configuration thing from CMake, and so I just didn't know exactly where all the files were. So it wasn't finding the shaders. Super funny, and it was just like, yeah, it's fine. You've installed it fine. Just turn it off and on again. I'm just like, that's like a meme. It's a comedy meme, but like it's still true, which made me laugh a lot. Oh, so Keth is asking, can you show us some past projects for this course so we know what we will be able to do? I cannot, because of two reasons. A, this iteration of the course has no past. And the second reason, this iteration of this course has no future either. That's a silly way to say it. But I haven't even written the specs for all the assignments in the course yet. I have a vague overview of what they're going to be. And the first one's going to have to get written really quickly, like in the next 2 days. Like, I'm trying to get it released on the weekend, at least. Maybe earlier, we'll see, but I don't think so. I think we're going to release the first one on the weekend. People probably have stuff from the last iteration of the course done in 2019, but it's going to be different from what we're teaching. It'll probably be similar, because last time it ran, I think it was a 10-week course last time it ran. So we're doing a 9-week course. They did a 10-week course. Before that, in 2018, it was a 12-week course, so it would have had more stuff in it. Either way, I think those previous assignments will tell you something. I will ask around, because I think Xavier will have some stuff previously. So Xavier is like the one person I could find who is still in CSE who tutored the course in its old iteration. So it's hard to say, but Xavier did give us the Nyan Cat from the last lecture, which is just an assignment 1. So he just did that based on the spec that I'd given the tutors about assignment 1, saying this is the kind of thing I want for assignment 1. And he was like, well, I can have some fun with this. And especially when I said that there was going to be percentage marks for subjective, artistic or creative content. He was like, oh yeah, I'm going to get into this. And he did that, right? Daniel said, show us chicken. Oh, chicken is actually here. Give me a second. It's like, this is what answering questions after the lecture is all about. Hello. She can tell when I started moving, her ears flicked up and she opened her eyes a little bit, but she's like, no, it's nap time. I don't want to talk to you. David said, I think Mark doesn't have access to past projects since the last offering 2019 was taken by someone else. That is true. I do have some access to the previous stuff. Like I've got things like old lecture slides and tutorials and stuff like that. But I actually haven't used very much of that. I haven't stolen much from the previous course, which I probably could have. But most of everything so far is being written off what I know in my brain about graphics programming, which is going to run out pretty soon. I'm going to have to I can only reel off stuff without thinking about it to a certain level. And then when I'm actually coding it, I'm going to have to be like, wait, write some code, remember the order these things should go in, and then teach it. So we'll get to that during term as we go. Simon does still have the assignment 2 from 2016. It's written in Java, so there's no exact correlation between the code. But if you want to look at the visual output of it, it should give you an idea of what we're doing. Andy was asking, why don't we use Java for this course? I would say the reason we don't use Java from this course is it's not generally the done thing. So usually OpenGL is paired with C++. You have to put some effort into pairing OpenGL up with Java. So it's like it's not 100% supported, and I prefer doing things the way that it's generally done. I mean, it's still a compromise. The C++ we're using is a compromise, but we found a way to make C++ reasonably machine independent in a sense. Like C++ by its nature is not a machine independent language, but when you use CMake, you can write, and if you use CMake and you set the project up in a certain way, you can make it so that you can submit code to us for your assignments, and we can actually compile it on our hardware and get a similar result to what you're getting and be able to mark it and stuff. So with that, I was able to achieve one of my goals, which is get you close to genuine graphics programming, which is usually done in C++ when it's OpenGL. Actually, DirectX is, I think, also generally done in C++, while still making it accessible enough that you can learn it and use it. Also, I figure in CSE, doing C++ is reasonably comfortable for a lot of students because C is the basic language for the computer science degree. Anyway, I don't know if that was a longer answer than you needed for that. Simon's like, if I pay him, he'll rewrite it in C++. I don't think that's the best use of your time. I have actual work for you to do. Hex has just realized that my chair is the IKEA Marcus. That is incredibly well spotted. That you can tell what a chair is. Just from its shape. And yes, it is. I laughed so hard when I was buying a new chair. It was years ago. It was like pre-pandemic, I think. And I sat in it and I was like, hey, this is reasonably comfortable. I looked at the tag and was like, the chair is called Marcus. That's it. We're buying it. It was like, yeah, so I find it reasonably comfortable. It's good enough. It wasn't too expensive. It had my name on it already, so I bought it. Very, very funny. And someone else is like, did you notice his Game Jam 2012 t-shirt as well? Yes. Important point. This Game Jam 2012 t-shirt, the grey t-shirt as opposed to the black t-shirt, I was one of the volunteer organizers of the Game Jam. So this is a very rare t-shirt. I mean, it's rare enough for being a Game Jam from nearly a decade ago, but it's also rare because only about, like, you know, there's a couple of hundred people doing it in Sydney, I think. It was a big one that time. But there was only about 20 or 30 of us who were wearing the grey shirts. Someone else is saying you can leave CMake alone and just use Visual Studio. Yeah, Visual Studio has CMake in the background. I don't know if that's necessarily leaving CMake alone, but that's knowing that your IDE actually came with CMake pre-built into it. Oh, Hexus, you recognize the chair because you have exactly the same chair. Richard is asking, would we still have to set up a few things and go through the entire GitLab guide if we wanted to use VLab? Well, I think Simon has potentially answered that But one of the big issues that we have is that VLab is CSE running a big bank of compute. Big bank of compute. Is that English? I don't know. Well, it kind of is, because it's several very big CPUs, like multiple CPUs, that serve the capacity of a CSE lab computer to you. The only problem with VLab at the moment is it's not necessarily hooked up to any graphics hardware. I think sometimes it can do some graphics stuff, but because it's not necessarily hooked up to any graphics chips, you can try to run OpenGL on it and it just does weird things, or it doesn't do anything. We haven't tested it excessively. We've tested it enough to know that we don't think you should use it. We can't rely on it to reliably render graphics. I would suggest that the best thing that you can do is render it on the computer that's physically closest to you, because then you're actually working on the graphics hardware in the computer that you have. And it depends whether that's like integrated graphics or whether that's a graphics card because you have like a gaming computer or something like that. Even plenty of non-gaming computers have graphics hardware in them, and it's enough to be able to run OpenGL. We've actually dialed back the version of OpenGL to be specifically compatible with as much stuff as we can. So it needs some modern stuff. So we're in version 3.3, if I remember correctly. You can tell by our shaders. Version 3.3. So this version has decent compatibility across the three main operating systems that we're looking at. I think 3.3 is necessary for us to hold to a certain level because of macOS. I think after a certain point, macOS just went, we're not doing OpenGL anymore. I was like, what? Okay. But modern enough that it's got a lot of things that we want to do, but far back enough that it's still quite compatible. So this isn't what you would use if you were making a current or a next-gen game. If you're starting out a new game project right now for the PS5, you would be like, there is no way we're using 3.3. We'll be using, what are we up to now? 4.1? Something, I can't remember what the current OpenGL version is, but we would be using something super spanking new. The only problem is we use something super spanking new, we lose compatibility. So we've chosen this version for having enough of the modern features that we can teach you, but also being far back enough that we get good compatibility. We are unlikely to get any of that compatibility in VLab. I guess I would have, in a sense, had the option to talk to the computer support group at CSE and ask them what kind of graphics capability VLab could have. But knowing what the hardware is on those things and the time frame for buying new hardware to serve, thousands of students at a time, I knew that there was no chance that they were going to upgrade that to have graphics in the near future. So I didn't want to burden them with that. And I opted for, let's make a decent setup that nearly anyone can put on their own computers. We were actually going to get a lab in CSC that was made for stuff like this. It was going to have some really, really beastly powerful computers, with things like new i9s and 3090s and stuff like that, in a really, really high-end gaming machines. But pandemic, we got locked down. The lab is still in a state of planning, not even being built. The machines didn't even get delivered before the start of this term, even though I think if we hadn't been in lockdown, they would have happened. And then you would have had access to these things. If we'd been in person, all of the tutorials would have been taught in that room as well. So there was all these things that would have been really cool. But yeah, as it is with us teaching from a lockdown situation, remote teaching and stuff like that, what we've got is a software setup that should work on nearly any computer. Even integrated graphics, this setup should work. Saketh's asking, can you show us what kind of games you made? Want to know what's possible for one person or a small team? Well, this is a difficulty, right? Um, can you show code that you wrote in 2000? For me, because I went into like organizing the game jams, I've got a game that I made in 2010 with a group of 5, 6 of us in 48 hours. Um, but I don't even know if it runs anymore, and I haven't tried to run it in years. I can give you a link to it and see if you can get it running. Where is it? Oh, how am I gonna find this? Global Game Jam 2010. I know that this is one of the ones that God, this is gonna be hard to find. I probably should have picked a country. No, no, it's not there. Oh, they don't have it anymore. Oh, that means I don't have it anymore either, unless it's on one of these hard drives that I have lying around my house somewhere. Okay, so it's gone. It's very much harder for me to show you something now. So this is talking about Game Jam games, but I haven't really made anything since then, other than like not me working as a dev, but me producing other people in small groups doing things. But we made this game called Spyware, which is spy, but like instead of WARE, it's WEAR, and it was about being a spy in this city, and you would go and change clothes and stuff so that people didn't know who you are. And it was a multiplayer game with these multiple little people walking around this 2D map, and you'd build up dossiers of your opponents. It was all on, like, everyone could see the same screen, and so you could see the idea of who other people might be. So you might get some information popping up that one of the spies is wearing a yellow hat, and then you'd go around trying to find the people with the yellow hat and hunt them down and stuff like that. So it was about changing clothes in order to hide from things, and there was all these NPCs on the map, and we constrained your movement so that it wouldn't give away who you were, whether you're an NPC or not, because everyone walked straight on footpaths and then took turns. So that was the concept of the game. We did it all in Python, and we had the most hilariously convoluted graphics pipeline I've ever seen. It was really funny. You could tell we were inexperienced at this stuff, because we had some people who was it one of them one of them works at Wargaming now. Another one worked at Animal Logic and Fuel VFX and Animal Logic. Um, what was the other one ended up? I think he went to the UK to work on films. So our artists were like super, super high end, and they did everything in 3D. So they had this full 3D city built, and then we just tipped it up and took a photo, a render photo of it from top down, and then made it into a sprite and plastered it into the game. It was so funny. It was like we did 10 times the amount of work necessary, and it looked cool, but we only ever had it viewing from one perspective. It was very, very silly. Anyway, um, what other things people saying? Yeah, so OpenGL 4.6, and in terms of kind of low level coding, Vulkan, as Simon's saying, has largely superseded OpenGL. So we expect over time that things are going to shift to Vulkan. Commercial game dev is probably still going to be using Direct 3D for quite some time, I expect. Especially because when it comes down to it, games are only occasionally going to be written with stuff like we're doing here. Like this, me editing the shader like this is going to be very different from what an artist lighting designer in a game is going to be doing nowadays. Ooh, Shader Forge? No, I don't know if I'm looking at the right thing. Yeah, Shader Forge for Unity. Yeah, it is Shader Forge. Come on, I just want the image. I just want to show. I'm trying to show my students the image. Do I open image in new tab? No, that's the thumbnail. There was, oh, here we go. This is what editing shaders looks like nowadays, where you don't write code anymore. You connect things up to each other. If you understand the code, you know what these things mean. But nowadays you can, as an artist, you can get into this stuff without knowing what the code was underneath it. So we are actually going to be doing diffuse and specular. We're going to look at normals and stuff like that. We're not necessarily going to do emission, transmission, and things. So like there's a limit to how much we can do. This is like decades of research has gone into this stuff. So can't cover that in a introductory course. But you know, colors, multiply. So this is like bits where we say color only comes up in certain places. We multiply by that, and all this stuff that you could write in code in shaders nowadays is more likely to be in a layout like this. So heaps of game development now has moved away from writing code in a text editor. I mean, Unreal Engine blueprints. Oh my god, look at that. Let's take one that might be easier for us to see. Coding in this kind of layout. Each one of these individual blocks is like a C++ function. If you want to, you can pull these things apart and rewrite what's in those blocks. So that way you can make sure if you want to really hyper optimize things and stuff, you can still do it in this system. Like game engines still recognize that optimization is super important. But plenty of games are being made where programmers are crossing over to coding in these things. Like I've had people who I taught the same things that I'm teaching you, which is all of like coding, low-level graphics coding and stuff like that. But when we say make a game in a month or something like that, or even worse, make a game in 48 hours, we jump to this stuff because it's just so much quicker. You can just drag and drop things and just go, look, I know how to make that. But if I'm counting the number of hours I have, the time it takes me to drag and drop this box in here. Also, actually, some of these are custom made anyway, so some of these were coded in advance. But something like this, lerp, linear interpolate between one thing and another based on something else. Great. Drag and drop that. I know how to make it, but I don't always have time to make it. So sometimes, like, I just assume that someone else also has probably optimized theirs, so I'll just use theirs, you know. So that kind of thing is the stuff that we're getting nowadays, which gets you closer to game with less effort. And also the idea that designing an interface for programming that I don't want to say that we're successful at this yet, but that a non-coding game designer can understand, or a non-coding technical artist can understand. So I had friends I was working with, because I would work alongside people of different disciplines. So game designers are like basically psychologists. You know, how do we get humans to believe something, right? And so they would work in this system. They would be able to get like a character moving around and stuff like that. And they would come to me and go, how do we do this? And I'd be like, ooh, that's going to be more complex. I will write a custom thing for you. Then you drag and drop it in. Or it's like, how can I get the camera to stop clipping through walls? And you'd be like, nope. In-game cameras are like just like a portion of hell brought up to Earth. For us to be forced to inhabit as games programmers. But anyway, Lorenzo saying could have had such good LAN parties in the graphics lab. Yeah, I joked about that graphics lab that I was going to suggest that we would repaint all of the walls and the windows, because we don't want natural light. Just paint everything black and all the lights be replaced with RGB. So we would just like the whole lab would look like the inside of this computer. Probably not conducive to a learning environment. Aaron, the head of school, has this face he puts on whenever I say stuff like that. It's pretty funny to make that happen. Oh, Yuntron is having some issues with the Windows setup process. Kaichi said he has a potential solution to that. The CMake video has some information for that. But I'll let you sort that one out because I think this is like something that we can't necessarily deal with right now with me on stream. um, RPG Maker, yes, also very easy to use. There's heaps of things, heaps of engines that make games easy. So stuff like, for me, the two big ones are Unity and Unreal. Um, Unreal is really taking off nowadays as the de facto game engine. Plenty of really, really high-end games are using Unreal Engine as their base. Um, you can drag and drop an entire game system into Unreal. So you can basically drag and drop first person shooter into Unreal and then throw assets into it, and then you get PUBG. Literally, you get PUBG. Um, the initial builds of PUBG, when they started selling it, basically had free random assets from the Unreal asset store. So free royalty free assets for like guns and stuff like that. And the people that made them are just like, oh, they just used my cheap throwaway 3D model and then they made several $billion and I didn't get anything because I sold it as a royalty free asset. So they made like one of the biggest games in the world. With just random stuff they could cobble together basically for free in the Unreal Engine. Like it's amazing the level of resources available to us nowadays. Henderson is asking how this course is going to give marks to you. So there's a particular layout for the marks, and all of the marks are in assignments. So the 3 assignments, 20% for the first one, 40%, and 40% for the next 2. If you want to break down of the course in more detail, the first lecture has a bit. Otherwise, the course outline here has more, and it has like the actual stuff that we're going to be doing each week and things, as well as a vague idea of what's going to be in the assignments. Simon's adding that, yeah, engine programmers generally make custom make tools. Yeah, so it's like that kind of thing where, like, as I was saying before, when I had a friend working in this who cannot code, but he's very, like, I'm thinking of a specific person here. He was very, very good at saying, I want these numbers to balance so that I can get this right feel. I want this feedback loop for my players. If I did a setup like this and said, here are the bits that you can change to do, like, kind of, I don't know, health versus damage or something simple like that, you know, he would be like, sweet, I'm in. And then I could walk away. Whereas if I had said to him, here is a C++ file, and here are the variables for damage and health, and here are the functions that change damage and health, I could, I think, quite correctly assume that when I come back in a couple of hours, I will have to delete that file and rewrite it. You know, like, I'm not going to throw someone into C++ like that, but I can throw someone into something like this, which compiles to C++, and I can actually open up each of these boxes and rewrite the C++ if I want. But someone who doesn't know it can still make changes in this without breaking it. So I find it quite useful. I think it's really cool. I have a feeling that a lot of this is the accessible nature of programming in the future. Because you think about it, all the programming we teach at an accessible level, so kids in schools and stuff like that, is in building blocks and stuff, and it's not raw text editing the way that we would do it at a more advanced programming level. So it's interesting. We'll see in the future how this shift happens, and whether, I think there will be a turning point where we consider someone who cannot use the system of brackets and semicolons and line by line text program. They literally cannot do that, but we will consider them programming literate. In the same way that we are approaching at the moment a point in humanity where we consider literacy the ability to be able to type and not write. So we could reach a generation of humans who cannot write with a pen and paper, but we consider them to be fully literate. And when we consider that, that's when the convention has shifted from one thing to another. You know, like, I assume that none of you are very good with a wax tablet or with a slate. but are fine with a pen and paper. You know, the technology moves on, and we consider the basic literacy to be with that, not with the older tech. Interesting though. Let me see. Hexus, can't wait for the UNSW course for Roblox game engine game dev. I mean, could very easily do a UNSW course on something like Unreal Engine. I would have to do so much work to get up to speed on that before I could teach it. But you know, like it's viable. And then you start to teach production, which is slightly different from programming in a sense. You start to teach how do you, because if you can get a finished product so easily, if your first prototype, your hello world, is what amounts to a finished product in a sense, we'll be teaching how to refine that finished product, how to meet deadlines and how to create content for it, that kind of thing. Could be interesting. Edward asks, what's the relationship between Unreal and Epic? Epic made Unreal? Or owns Unreal? It's the same thing. Epic is the company that made the Unreal Engine. So they're very, very closely linked. Fortnite was an engine demo. They accidentally made one of the biggest and most famous games in the world by doing an engine demo, which is the reason why it runs on every platform. So for them, it was a matter of honor that it must run on phones, it must run on Nintendo Switch, it must run on all consoles, must run on all PCs, you know. So it was a selling point to get people to use Unreal Engine for things. It's like you can drag and drop the same game into multiple systems. And then it turns out they didn't need to sell the engine anymore because they've been making so much money just from the game. It's weird. Epic hasn't made many games. It's just a couple. But they've made so much money out of Fortnite. But again, they've made so much money out of the engine. So everyone that uses Unreal Engine for all their AAA games and stuff like that are paying money to Epic. Simon, the rich don't innovate. Remember that? Yeah, that's a thing. Oh, Henderson, you only just enrolled yesterday, right? Okay, so hopefully you can go back and see some of that content before you get too deep into the course. But I have kept the assessment structure reasonably simple, so hopefully it's not going to be too confusing. I didn't really want to make a super confusing course with lots of little things. Logan's asking, are they still making Unreal Tournament? I don't know. I know they did something with Unreal Tournament recently, but I think that was like a remaster or something like that. But it's not really that much. You see a couple of companies who have made a great deal of money out of other people's games, in a sense. So I'm looking at Valve and Epic. They used to be game development houses. Like Unreal Tournament was, you know, a big, genuine game. But then they realized that their expertise was more in tech than it was in game development. Because to be a great game developer, you need a whole different set of people than an engine developer. The engine developer is all technical. So it's all like, when we think about programmers, you know, it's like people like us who's like coders. But to make brilliant games, the key element is not your coders. The key element is your designers, your human experience game designers, right? Your storytellers. Because you can have technically god-awful games that tell amazing stories and people will buy them for years and years. Looking at you, Skyrim. You know, right? Skyrim is like technically so poorly done that the user-made mod that patches the game is something like 4 or 5 gigs. It is so huge. The stuff that just fixes all these little issues they left in the game. It's gotten to the point where Bethesda doesn't think they have to polish their games anymore. They can just release it and let the community on Nexus mods polish it for them, right? But yeah, so some companies have just gotten really into the tech side of things, and they're fine. They've survived quite happily on that. Unreal and Epic are thriving on the fact that they've built a system that makes it so easy for other people to make games that everyone wants to get involved. And I like their education perspective as well. They're like, if you're using this for education, you pay nothing. You will never pay anything if you're using this to teach people. But that's their way in, because if everyone has learned how to use it, then they're going to want to use it when they go to try to make money out of it, right? It's just such a smart, it's like slightly insidious, but also kind of nice in a sense, as opposed to like everything that like Adobe makes for making art. They're like, nope, you have to pay for everything. And so it's funny that the game development side has all these free tools, because they know that like when you make it big, you'll pay us. So they have this clause which is like, you have to make over a certain number of thousands of dollars, and it's like, you don't start paying until you've made like $5,000 or something like that. I don't know exactly what it is or which currency that 5,000 is in, maybe US dollars. But it means that like for us, just use it, you know, and we use the fully featured program. But once we put it on Steam or we put it on an app store or something like that, and we start getting revenue, then we'll pay them. And so it's a really, really friendly kind of developer license for us learning about things. But then when you're actually making big AAA things and stuff, you're paying them so much money. So it's interesting. They get their money from the right place, because there's no point trying to make money off students, because how much disposable income do people have when their full-time thing is something that they have to pay for and eats up all their time as well? Anyway, I've been talking for ages now. And Sam's also saying, gotten so many free games from Epic, haven't paid them a cent. Yeah, we're just assuming someone else is paying money. Epic is owned by Tencent as well now, which is like one of the biggest sort of mega corporations in the world. So even if they start having trouble and stuff, I'm pretty sure their Tencent overlords will be able to be like, here's a bucket of money, now get yourself back into shape and then you'll be fine, you know? So sometimes I think having that giant money backing behind things can sometimes give you support. At other times they shut you down without telling you why. So we'll see how that goes. For the moment, I think Epic's in a very safe place. Yeah. Oh, Edward's talking about Blizzard. I don't know. Blizzard's in a really weird place at the moment. Blizzard used to be a company we held up as this bastion of design, and a company smart enough to delay its releases to make sure that they were good, and only release things that were good, and be really careful with everything and stuff. But lately, I don't have a lot of trust. Like, just morally, the upper level management of the company seems to have gotten so full of themselves in their own godlike status that they've stopped treating humans like humans. So there's big issues there. And also the stuff they're doing technically, their remakes of their games are falling flat because they're not paying respect even to their own content. Anyway, let's not. I could deconstruct Blizzard for hours if you wanted me to, because I used to worship them, and now I have only disdain. So it's a mess. Yeah. Oh, JT was like, doesn't that technically mean UNSW has to pay if we're using Unreal? I think the licensing for Unreal allows education. The only thing they talk about in terms of revenue is revenue from games released with Unreal Engine being used, not necessarily revenue made from teaching people Unreal Engine, because I think they also know that you don't want to block that. Like, if they put a barrier in place for people teaching other people how to use Unreal, then what they end up with is less people knowing Unreal and less people wanting to use it later when the money starts flowing in. So I think they're clued onto that, especially because the second they charge students to use Unreal, everyone will just switch over to Unity, and then Unity will end up the big engine as opposed to being the second engine as it is at the moment. Okay, I'm gonna wrap it up there. I've gone like 45 minutes over the lecture time, but I do like doing this. I do like having a chat afterwards, which is fun. It reminds me of hanging around outside the lecture theatre afterwards I remember even like back when we were teaching in person, I would go to lunch somewhere, and then some of the students would just turn up at the same lunch, and we'd just be like, "Oh, well, we happen to be eating at the same restaurant on campus. Let's have a chat, talk about the course and stuff like that." Um, so this bit after the lecture always reminds me of that, even if it's only me talking. There's a little bit of chat there. I was actually thinking of moving this post lecture thing over to Discord, but it's hard. Like, I guess we could all sign on to chat on Discord and talk about things. But we'll see. We'll see what we do. I'm not like, especially this informal kind of afterwards bit. I'm not really not going to put a huge amount of effort into organizing this in a specific way for like educational goals. You see the huge difference between like my lecture slides and the layout of the 2 hours is really, really specifically put together. That's where all my time and effort goes into. This bit afterwards, I'm just like, I'm not gonna go spending days developing a system in which we have an informal chat after the lecture. All right, I should wrap it up there. Thanks everyone for coming along. Hope your tutes are fun. Hopefully I've still left you an hour now to do the setup if you need to and have some lunch. For those of you who are on the first tute at 2 p.m. I think there's 2 tutes at 2 p.m. I can't remember for certain. I will... What's Michael saying? Oh yes, CSE was building a collaboration space at the bottom of K17. I mean, yes, but at the same time, no one's getting in there now anyway, so what are you gonna do, right? I think everything's on pause in terms of like useful spaces and stuff at UNSW until we can all get back there in significant numbers. I think the only people at UNSW now are people whose work can't happen outside of specific labs, and obviously us in computing, we just do everything remote. Okay, see you all later. Have fun in your